Guys, look at this mess. You know what it is? It can only be one thing. The gamma function. But all kidding aside, this really is a complicated topic. And don't worry if you didn't get it the first time that you heard it in class. A lot of the students that I've tutored had trouble with it, but as you'll see in just a minute, it's really not that hard. You're in the right place to figure it out. So a factorial in its general form is written like this: any number n with an exclamation mark. And this is equal to n times n minus 1 times n minus 2 and so on and so forth times 3 times 2 times 1. And it's only for natural numbers, obviously. So let's take a look at an example. Something like 4 factorial is what? It's 4 times 4 minus 1 times 3 times 2 times 1. And that gives us what? 4 times 3 is 12 times 2, 24. Right? So let's keep going. 3 factorial is 3 times 2 times 1 gives us 6. 2 factorial is 2 times 1 gives us 2. 1 factorial is just 1. And 0 factorial is also 1. Why is that? I have a good explanation for you. So let's take a look at 3 factorial. A factorial is just a combination of how many combinations we can make with something, right? That's the physical interpretation. So if we have 3 markers, we can rearrange them in 6 different ways, right? First orange, then pink, then purple, first purple, then orange, then pink, and so on and so forth. There's 6 ways to do it. If we only have 2 markers, there's only 2 ways to rearrange them. Orange and purple, purple and orange, right? Just 2 ways. If we have 1 marker, obviously there's just 1 way to arrange it, right? 1 factorial is 1, it's just this way. But if we have 0 markers, there's also just 1 way to arrange 0 markers, right? That makes sense. That blew my mind when I first heard that explanation, but I think it makes the most sense. Now, another interesting thing is 52 factorial. Why 52? Because there's 52 playing cards in the deck, right? Well, 52 factorial is a huge number. I don't even know what it is. It's huge. You can, if you have enough time, put it into Wolfram Alpha, write it in the comments. If the comments will even let you write that many characters, because this is huge. But the cool thing about this is, because every time you shuffle a deck of cards, you have a 1 over 52 factorial chance of getting that particular combination of cards when you shuffle it. That means that chances are, anytime you shuffle a deck of cards, and you shuffle it nicely, not just like rearrange 1 card, but if you shuffle a deck of cards, it probably means that's the first time in human history that a deck of cards was shuffled in the way that you just shuffled it, because this number is so huge. Think about that. That's pretty crazy, right? So calculating factorials is easy if you're working with small numbers, right? Because if we have something like 6 factorial, we can just write it out. 6 times 5 times 4 and so on. And we can just do that by hand. But what if we want to know really big numbers? What if there was a function where we could plug in the number and instead of multiplying it out, we could just get the answer? Well, there is. Euler came up with it back in the day. And it's called the gamma function, Euler's gamma function. And you might wonder, why gamma? What happened to alpha and beta functions? You don't want to know. So anyway, the definition of the gamma function is the Greek letter gamma of the number n that you want to calculate. It is an integral from 0 to infinity, x to the n minus 1, e to the minus x dx equals n minus 1 factorial, right? So if we want to know some number, we plug it into here and we get the n minus 1 factorial, right? So let's give it a try. Let's calculate, let's plug in a number, calculate this crazy integral and see if we get what we want. So let's try 3, gamma of 3. We want gamma of 3, and that means 3 minus 1 factorial, which is 2 factorial, which is 2. So if we plug in 3 to this whole mess, we should get 2. Let's see if we're right. So let's get started. Gamma of 3 equals the integral of 0 to infinity. X, 3 minus 1 is 2, e to the minus x dx. Now, what do we do from here? How do we get this to equal this? Well, it's not that hard. Let's do it. So what we have to do is something called integration by parts. And how does that work? The formula is an integral of u dv equals uv minus integral of v du. What does this mean? So anytime in an integral we have two functions like we have here, we have x squared and e to the minus x, we need to figure out which one of them should be u and which one of them should be v. And using this tool, we can lower the power of x. That's really what we want to do. So in this case, we're going to say that u is equal to x squared. Why is that? Because here we have u by itself, but here we have du. So by doing the du, by taking the d of dx over x, we're going to lower the power with each step. So let's do it. So if u is equal to x squared, that must mean that dv is everything else, right? It's e to the minus x dx. And that must mean that du, the derivative of u, is 2x dx, right? Because we just take the derivative. And that must mean that v, the antiderivative of e to the minus x, is simple because it's e to the minus x. It's always the same, but with a minus sign. So it's minus e to the minus x, right? So we did the first step. Let's plug this back in. We have to use this formula for these numbers that we have. Oh, and by the way, I'm using these vertical equal signs. Obviously, it doesn't equal. It's just like a substitution. I always use this in my calc classes. I thought it was pretty helpful. So let's plug everything back in. We have the uv, right? So we multiply u and v. It's minus x squared e to the minus x, and it's from 0 to infinity, right? We can't forget about the limits of the integral. Minus the integral from 0 to infinity, because that's what we're working with, v du. What do we have for v du? We have minus e to the minus x, so we can just change this to a plus. We have e to the minus x, and what is the du? It's 2x dx times 2x dx, right? You see what we did there? We had x squared, but now we just have a regular x. So what do? We do this all again. We use the same integration by parts, but this time our u is just the x here, right? Because we want to lower it even further. We want to get rid of it completely, right? U is dx, so that must mean dv is once again, what? E to the minus x dx. I'm ignoring the 2 because we can just write it out. We'll put it out in front of the integral. So that must mean du is what? Du is just dx, right? And then v, the antiderivative, is once again the same as we had before, right? Because this is the same thing. E to the minus x doesn't really change. So v is minus e to the minus x, right? So let's plug this back in. What do we have? We have the first part, minus x squared e to the minus x from 0 to infinity, plus this whole mess. So we open up the parenthesis, and we have the same formula. uv, u times v, so it's minus x e to the minus x minus, what do we have? Minus the integral of 0 to infinity, oh, and this is also 0 to infinity, can't forget that, of v du. And what do we have v du? V du is just e to the minus x dx. The minus sign is right here, and the 2, where was the 2? The integral of the 2, so it should be here, right? Because we had the 2 of the integral here, then we substituted in the integral, did the integration by parts, and this is what we're left with, right? So let's write all of this out and see what we get. So we have equals, let's keep going. We have equals minus x squared e to the minus x from 0 to infinity minus 2x e to the minus x from 0 to infinity and plus 2 of the integral 0 to infinity of e to the minus x dx. Now, this is a pretty simple integral actually. Integral of e to the minus x to the negative infinity. What does that equal? Where can I do that? I have some space here, I'll do it. So an integral of 0 to infinity of e to the minus x dx is what? It equals minus e to the minus x from 0 to infinity, and this equals minus 0 to the minus infinity plus e to the 0. Does that make sense? E to the minus 0 actually, because we want to know the difference of when is this part minus e to the minus x equal when x is infinity minus when e to the minus 0. But because it's minus minus, it becomes plus. And what is this? This is 0 plus 1. Because e to the minus infinity, it's 0, right? The limit is 0, it just shoots off to nowhere. And e to the 0, anything to the power of 0 is 1. So this is 1, right? This whole mess. So let's rewrite that, and let's factor out e to the minus e to the minus x. Let's factor that out. So we have e minus e to the minus x. We open the parenthesis. What do we have? We have x squared plus 2x. This whole mess is from 0 to infinity. And then plus, we know that this integral is 1, but we multiply it by 2, so plus 2. Now you can probably tell where this is going. We already have the 2 here, which is what we wanted initially. So that must mean this mess must equal 0. Well, let's check if we're right or not. We have to do the same thing. First we plug in infinity into every x, and then we do minus this whole mess, but with zeros. So let's try it. Minus e to the minus infinity, which we already know is going to be 0. Spoiler alert, because it was 0 over here. Infinity squared plus 2 infinity, right? Now you guys might say, well, how do we know that infinity times 0 is going to be 0, not infinity? Which is heavier in this case, right? Which is more significant? The infinity squared or e to the minus infinity? Spoiler, of course it's to the minus infinity, because infinity is in the power. It's not just some measly infinity squared. If you have infinity in the power, it's always going to be heavier, so to speak, than anything else. So we know that this whole mess is equal to 0. And then we have to do minus this again, but because there's a minus sign, we do plus e to the minus 0 times 0 squared plus 2 times 0. And of course, even though e to the minus 0 is 1, because we're multiplying it by 0, this whole mess is equal to 0 plus 2, right? This is all equal. So in the end, we're left with 0 plus 0 plus 2. Now, isn't this a much easier way to do it than just multiply 2 times 1? Of course it's much easier. But believe it or not, this is how calculators do it. Or if you have some really crazy equations, nobody sits out and multiplies 347 factorial. You just pop it into the gamma function and you solve it like this. Obviously, nobody does it by hand anymore, because whatever the power you have, in our case it was 2, because we wanted to know the factorial of 3, right? And then the function, the gamma function of 3, we have x2, x squared. And whatever power x is the number of times that you have to do integration by parts, right? We did it once here and the second time here. So obviously this is going to get real messy if we want to know like gamma function of 8, for example. We're going to have to do 7 integration by parts, and that's just insane. That's something you're not even going to see on a calc final. I think the most that I ever had on a calc final was 4 integration by parts. And that was like, I don't even know, calc 100 in my senior year. So yeah, that's it. That's the gamma function. So I hope you guys like this video. Click like, click subscribe, and stay geekly, my friends.